Hello, and welcome to Controllerstech. In today's video, we're going to learn how to interface the R307 Fingerprint Sensor module with an STM32 microcontroller. The R307 is an optical fingerprint scanner that comes with a built-in DSP chip. What this means is that the module not only captures the fingerprint image, but also processes it internally. It takes care of converting the image into a fingerprint template that can be used directly. So the microcontroller does not need to handle heavy image processing or recognition tasks. Another key advantage of this sensor is its storage capacity. The R307 can store up to 1,000 fingerprint templates in its internal memory. With just a few simple commands, you can easily add new fingerprints, search for existing ones, or even delete entries when required. The communication is also very straightforward. The sensor uses UART, or the serial interface, which makes it widely compatible with different platforms. Whether you're working with Arduino, STM32, ESP32, or even Raspberry Pi, the module can be connected without difficulty. For this demonstration, I'm going to use the STM32 R307 development board from WeAct Studio. If you're located in India, you can conveniently purchase this board from shop.controllerstech.com. Now, let's move to CubeIDE and begin by creating a new project. As mentioned earlier, I will be using the STM32 R307 base development board. Give the project a suitable name, and then click on Finish to create it. The first step after project creation is the clock configuration. I will be using the internal clock source and setting it to run the system at the maximum frequency of 180 MHz. Next, go to the system settings, open the debug option, and enable serial wire debug to make debugging easier. Since the fingerprint module communicates through UART, I will configure UART4 for this purpose, as it provides a convenient connection option. Enable the UART in asynchronous mode. The R307 sensor uses a default baud rate of 57,600 bps. The word length should be set to 8 bits, with no parity and one stop bit. In addition to this, I will enable one more UART channel to display logs during testing. On this board, the UART1 pins are easier to access, so I will use them for logging. You can set any baud rate for the log UART, but I'm going to configure it to 115,200 bps. I'm also going to connect two LEDs to the board. These LEDs will serve as indicators. One will turn on if the fingerprint matches, and the other will turn on if it does not match. So in CubeIDE, set two pins as output mode. These will be used to connect the LEDs. That completes all the configuration we need in CubeIDE. Now, click on Save to generate the project code. Before moving forward with the coding part, let's take a quick look at the hardware schematic. Here we have the R307S Fingerprint Sensor module. Functionally, it is the same as the R307. The only difference is the size of the PCB. The connector on this module has pins labeled from 1 to 6. Let's go through them one by one. Pin 1 is the VCC pin. This should be connected to the 5V pin on the STM32 board. The good thing is the module automatically converts this supply voltage to safe TTL levels for UART communication, so it is completely safe to connect it directly to 5 volts. Pin 2 is the ground pin, and as expected, it should be connected to the ground of the STM32. Pin 3 is the UART TX pin of module. This pin must be connected to the RX pin of the STM32. Since I am using UART4, this pin will go to PA1. Pin 4 is the UART RX pin, which should be connected to the TX pin of the STM32. Again, since UART4 is being used, this pin connects to PA0, which is the UART4TX. The remaining pins of the connector are not required for our project, so we will leave them unconnected. Now let's look at the LEDs. I have connected two LEDs to pins PC0 and PC1. When a finger placed on the sensor matches with the data stored in the database, the green LED will light up. If the fingerprint does not match, the red LED will turn on instead. For debugging and monitoring, I am using UART1 to output logs. Here, the STM32 pin PA10, UART1TX, is connected to the RX pin of a USB to UART module, and this module is then connected to the computer using a USB cable. That's all for the wiring diagram. Now let's move ahead and continue with the project. Here I already have the library files prepared for the R307 sensor, and we will copy them into our project. Place the C file inside the source directory and a header file inside the include directory of the project. Let's begin by opening the header file. In this file, you first need to define the UART instance that you're using to communicate with the R307 sensor. This is important as the library functions depend on the correct UART configuration. If you run into any issues during development, you can enable debug logs by setting the debug variable to 1. With this option enabled, the library will print detailed logs for every step of execution, which is very helpful for troubleshooting. The main logs should always remain enabled, as they provide information about the user interaction with the sensor. For logging, I have used the standard printf function. This makes it easier for us to format and display the log data clearly on the terminal. That's all the configuration required in the header file. Now let's move to the source file and see the available functions along with their usage. The R307 Enroll function is used to enroll a fingerprint. It requires a parameter called page ID, which is simply the location number where the fingerprint will be stored inside the sensor's memory. The R307 sensor is capable of storing up to 1,000 fingerprints, with IDs ranging from 1 to 1,000. Next is the R307 Verify function. This function captures a fingerprint image and searches through the database to find a matching template. It has two parameters, outPageID, which returns the ID of the matched fingerprint, and score, which indicates how closely the captured fingerprint matches the stored template. Another useful function is Verify Password. This is used to verify the module's handshaking password. It takes the password as a parameter and returns how OK if the verification is successful. If the password verification fails, you can use the Set Password function to set a new password for the sensor. This function accepts the new password as its parameter. There are also functions to manage stored fingerprints. For example, Clear All Fingerprints will erase all the fingerprints stored in the sensor's memory. And the Delete Fingerprints function can delete a specific number of fingerprints, starting from any given page ID. To understand how these functions work internally, let's take a look at the R307 datasheet and scroll down to the section describing the command details. Here we can see the general format of a command that needs to be sent to the R307. It begins with 2 bytes of header, which is always 0xEF01. This is followed by 4 bytes of the module address. By default, the module address is set to 0xFFFFFFFF, but it can be modified using specific commands. Next, there is a 1-byte package identifier. This byte helps the sensor determine whether the packet being sent is a command packet or a data packet. After that, we have 2 bytes of length, which specify the total length of the instruction code, parameter bytes, and checksum. The instruction code comes next. For example, 0x13 is the instruction code for the Verify Password command. The instruction code is followed by parameter bytes. In the case of the Verify Password command, the parameters would be 4 bytes representing the password we want to verify with the module. Finally, we add 2 bytes of checksum, which completes the command packet. When the R307 receives a command, it responds with a packet in a similar format. The first 6 bytes, which contain the header and address, remain unchanged. The package identifier in the response is 0x07, which represents an acknowledgement packet. Then we again have 2 bytes of length, followed by the confirmation code, and finally 2 bytes of checksum. The confirmation code will vary depending on the instruction. For example, in the verify password command, the confirmation code can be 0 if the password is correct, 1 if there was an error in receiving the command, or 13 if the password is incorrect. Now let's see how all of this is actually implemented in the code. To keep things clear, I will take the example of the verify password command. The first step is to prepare the parameters. Since the password is 32 bits, we need to break it down into 4 separate bytes. Once the parameters are ready, we call the function build command to construct the final command packet. The function build command takes a few parameters. The first parameter is the structure where the complete command will be stored. The second parameter is the instruction code itself. Next, we provide the instruction parameters. And finally, we pass the number of parameter bytes. Inside the build command function, the process begins by inserting the header and the device address at the start of the buffer. After that, the package identifier is added. In this case, the identifier will be set to command. Next, the function calculates the total length of the command package. This length includes 1 byte for the instruction code, the number of instruction parameters, and 2 bytes for the checksum. Once the length is calculated, the function copies the length, the instruction code, and the parameters into the command buffer. Finally, it calculates the checksum. The checksum is obtained by adding all the data starting from the 6th position in the buffer. Once calculated, the checksum bytes are also copied into the buffer. At this point, the command buffer is complete and it is ready to be sent to the sensor through UART. Now let's see how these functions are used inside the main.c file. First, include the R307 header file, and then define a write function for redirecting the printf output. Here we will redirect all printf outputs to UART1, which we already configured earlier for logging. Inside the main function, we start by calling the function to verify the sensor password. The default password is 0. And if this matches the sensor's password, the function will return HAL_OK. If the verification fails, we will print the error logs on the terminal and then call the error handler function. In case the password does not match, you can also call the function to set a new password and then verify it again with the sensor. Once the password step is successful, the next task is to clear all the fingerprints stored in the sensor's memory. After clearing, we will proceed to enroll a new fingerprint at page ID 1. Here, the program will print a message asking the user to place their finger on a sensor. When the user places the finger, the enroll function will be called. This function handles the complete process. It captures the image, converts it into character data, and finally stores it at the specified memory location inside the sensor. If the process is successful, the function will return HAL_OK. Next, we move on to verifying a fingerprint. For this, we first define 2 16-bit variables, one for the match page ID and one for the score. The program will then prompt the user to place a finger on the sensor for verification. After that, we call the verify function. This function captures the fingerprint image, searches the database of stored fingerprints, and tries to find match. If a match is found, the match page ID will be stored in the variable we defined earlier, and the score will be stored in the score variable. The score indicates how closely the fingerprint matches with the stored template. The higher the score, the better the match. In general, a decent match will have a score of around 150 or more. That's all we need to get the sensor tested for the first time. So now, let's go ahead and build the project. The build is successful, and there are no errors. So the final step is to flash the code to the STM32 board. Now let's open the serial port that is connected to UART1 so we can view the logs from the board. I will reset the board once to start the process from the beginning. As you can see in the logs, the password verification is successful and the sensor has been initialized correctly. Now the program is asking us to place a finger on the sensor. The fingerprint will be stored at page ID 1. For this demo, I'm going to use my right thumb. You can see in the logs that the first image has been successfully captured and converted. At this point, we need to remove the finger and place it again. After capturing the second image, the sensor automatically merges both images and generates a combined template. That completes the enrollment process, and now the verify function begins execution. Let's place the same finger again. The logs confirm that a match has been found at ID 1, with a match score of 352, which indicates a very strong match. Now let's reset the board once more to test another case. This time, I will register the thumbprint again, but for verification, I will place my index finger instead. As expected, the fingerprint does not match the database, so no match is found. To make the sensor continuously check for fingerprints, I have placed the verify function inside the while loop. I have also added a delay of 1 second before each new verification, so the function will wait before checking the next fingerprint. Let's build the project again and flash it to the board. We'll first complete the enrollment process once more. Now, let me try verifying with my index finger again. Since this fingerprint was not stored earlier, there is no match found. Because the verify function is running inside the while loop, it immediately asks for another fingerprint again. Now let's try the thumb once more. And as expected, this time the match is found successfully. The verify function continues to run in the background, checking the sensor for new fingerprints each time. So far, everything is working exactly as intended. However, there is one important thing to note. Every time the system reboots, the functions for password verification, clearing fingerprints, and enrollment will run again. But we do not want to re-enroll fingerprints after every reboot. Instead, these functions should only run when we specifically need them. To achieve this, we can use UART commands to decide which function should run at runtime. Although I am not implementing full UART control here, I will simply block these functions after the first run. One way to do this is by storing a value in the flash memory and checking it during runtime. But since writing to flash requires more effort, I will use a simpler approach. We can take advantage of the RDC backup register, which I also explained in detail during the RDC tutorial. So let's go back to CubeMX and enable the RDC peripheral. Do not enable anything else, since we only need its backup register functionality. Now I have replaced the earlier code with the updated logic. First, we define a variable to store how many fingerprints we want to enroll. At the beginning, we will verify the sensor password as usual. Then, we will check if the RDC backup register already contains this value. On the first run, this value will not be present, so the code inside the condition will execute. Here, we will first clear all the stored fingerprints. Next, we will run the enrollment function for as many fingerprints as needed. Since storage in the sensor begins from page ID 1, the loop variable should also start at 1. I have also added retry functionality, so if enrollment fails for a particular finger, the program will attempt it again. Once the required number of fingerprints are successfully enrolled, we will write the value into the RDC backup register. This ensures that enrollment will not run again the next time the system reboots. After the initial setup is complete, the program moves to the main verification loop. Here, we continuously call the verify function, and based on its result, we control the LEDs. First, we define the LED ports and their pins. If the verify function does not find a match, the red LED will turn on to indicate failure. Otherwise, if the fingerprint matches, the green LED will turn on, clearly indicating that the match has been found. After this indication, we will wait for about 2 seconds and then turn off both LEDs to reset the status. Let's build the project now. It looks like there is a small error in the pin definition. Let me correct that and rebuild the project again. Now everything compiles successfully, so let's flash the code to the STM32 board. First, I will enroll my right thumb. The thumb has now been enrolled successfully and stored at page ID 1. Next, I will enroll my right index finger at page ID 2. With both fingers stored, let's go ahead and verify them. As you can see, when the correct finger is placed on the sensor, the green LED lights up, confirming the match. Now let's try with my left thumb. This time, the fingerprint is not found in the database, and therefore the red LED turns on. I will try with my left index finger as well. Again, there is no match, and the red LED turns on to indicate failure. But when I place the correct registered finger again, the green LED turns on once more. So everything is functioning exactly as expected, and our fingerprint sensor is working perfectly. In addition to what we tested here, you can also make use of many more instructions available in the datasheet. For example, if you want to enroll multiple fingerprints from different people at different times and store them all, you can use instruction 7, which checks whether a template already exists at a specific page ID. If the template is present, the function will return OK, and you can skip storing at that location to avoid overwriting existing data. Similarly, instruction 15 allows you to change the device address if needed. Now let me quickly show you some of the additional functions available in the library. One such function waits for a finger to be placed on the sensor. It uses a timeout feature, so if the user does not place their finger within the given time, the function returns a timeout error. Inside the enrollment function, I have set this timeout to 20 seconds, giving the user enough time to place their finger on the sensor. There's also another function which waits for the finger to be removed from the sensor before continuing. As I mentioned at the beginning, you can enable the debug logs to print detailed debug level messages on the console. These logs are generated from inside the static functions and can be very helpful in identifying and debugging any issues with the sensor. So with this, we have successfully interfaced the R307 Fingerprint Sensor with an STM32 microcontroller using the UART interface. The sensor can store up to 1,000 fingerprints, which means it is suitable for projects where you need to register a large number of users. You can also extend this project by controlling the sensor's operations using UART commands, or even building a GUI on a display to make it more user-friendly. Let me know in the comments if you would like me to create a video demonstrating how to use the sensor with a GUI interface. That is all for this video. You can download the complete project from the link given in the description. If you have any questions or doubts, feel free to leave them in the comment section. Thank you for watching, and have a nice day ahead.